This question is about continuous time signal, and we're asked for the Fourier transform. So the first part gives us a cosine and asks us to sketch that in the time and frequency domains. So we need two sketches, a sketch of x of t and a sketch of x of omega. So the sketch of x of t will be a function of time, and the sketch of x of omega will be a function of omega. So to get the mark, you need to annotate the axes. So each of these is necessary to get the full mark. Next, even though it's a simple cosine, we need to know the period. So if we know omega to be 10, then the period is 2 pi over 10. So we need to sketch a signal with a period of 2 pi over 10. So it's a cosine. So an approximate sketch like that is fine. You need to label the amplitude 1, and we would need to label these zero crossings. So this is the period of 2 pi over 10, or pi over 5. This would be half that, so pi over 10, and this would be pi over 20, and this would be minus pi over 20. And here you'd have 3 pi over 20. So that's what you would be expected to show for the first plot in the time domain. Now for the frequency domain, you need the Fourier transform of this. And you can look this up in a table if you're provided. In this year's exam, you won't be provided with a table, but you should know that the Fourier transform of a cosine is simply two impulses. So a symmetric pair of impulses at plus minus omega naught, which will be 10, and minus 10. And the height of these impulses will be pi. Now you could put the pi there if you like, that's fine. Is it necessary to show the negative side of the frequency axis? Yes. If you're asked for a frequency domain plot, you have to show both sides of the axis. So that's all you need for part A, for the 5 marks. Part B is about an entirely different signal. And we're given this Fourier pair. We're told that a single-sided exponential has a Fourier transform that looks like that. And we're asked to show that the Fourier transform for the double-sided exponential looks like that. So really our problem is expressing the double-sided exponential as a function of the single-sided exponential. So if you think about it, the absolute value there of t, we can simply represent that like this. So we can say x2 of t is equal to e to the minus at if t is greater than or equal 0, or it's equal to e to the minus a minus t if t is negative. And that just means e to the at. Now, t is positive, we can rewrite that as u of t, or multiplied by u of t. And t less than 0 is like multiplying by u of minus t. So remember, u of minus t looks like this. So now I can write x2 of t as a single expression, and I can say, let's start with the negative time. We'll say it's e to the at times u of minus t plus e to the minus at times u of t. So now I have a nice expression for x2 of t. We can use that to find the Fourier transform x2 of omega. So the Fourier transform by definition is the integral of x2 of t e to the minus j omega t dt. And we can split that into two integrations. We can say it's the integral from minus infinity to 0 plus another from 0 to infinity. Now this second bit we don't need to worry about. That is exactly the same as the Fourier pair that we're given in the question. So we can simply replace that with 1 over a plus j omega. So I'll do that now. Now, this bit, I can replace x of t with what we just, what the value is for negative time. So it's simply e to the at times u of minus t. And u of minus t is simply 1 for this range. So I can remove that. So now I have that expression there. Now, if we employ a change of variable, if I say v equals minus t, I can then rewrite that as a function of v. I can say it's e to the minus av times e to the minus j omega v. Positive d v, and then there would be a minus there. And if you either carry out that integral or use the pair we have given, the result is 1 over a minus j omega. So we can rewrite that as 1 over a minus j omega. So we have one more step to go. What we're trying to do is to show that this is equal to that. So we can't leave it in that form. So we can find a common denominator, a minus j omega times a plus j omega. And then you'd have a plus j omega plus a minus j omega. So that cancels with that. That gives you 2a over a squared plus omega squared, because these are complex conjugates. So that's the same as the expression we are looking for up there. So that's the answer for part B complete. Now for part C, we're asked for a sketch. So it's asking for two sketches, a time domain and a frequency domain sketch. So x2 of t was our double-sided exponential. So we simply, let's just remind ourselves what that is. So that's e to the minus a absolute value of t. And the function of omega is 2a over a squared plus omega squared. So we want two plots, one as a function of time and one as a function of frequency. x2 of t, x2 of omega, t, omega. So our plot, it's a double-sided exponential. It would look something like this. And we need to label that point there as 1. So to get the full mark, you would need annotated axes and that value 1 there. x2 of omega, because it has a omega squared in the denominator, the signal would look something like this. So as omega approaches infinity, this would approach 0. And this point here is when omega is equal to 0. So that would give you 2a over a squared plus 0, which is 2 over a. So you'd label this point here 2 over a. So to get the full mark, you would need to label the axes, you would need to indicate that point, and you would need to show the general shape of the spectrum. So that's part C. Moving on to part D, another set of sketches. We're asked to sketch the product of x1 and x2 in the time and frequency domains. So let's remind ourselves, what's x1? That was just the cosine, wasn't it? So that was my x1, and x2 was the double-sided exponential. So if I multiply the two, how will that look in the time domain? Well, let's attempt to do that. So you'll need a time axis. You'll need to label it y of t. That's important. Let me use another color. You'd have an envelope like that. And then you'd have your actual plot. So your plot would be a cosine, the amplitude of which is restricted by this envelope. And then you don't need to keep the envelope because that's not part of the answer. So if you were to keep it as a dotted line in the exam, that's fine. But it isn't part of the plot. The plot is only the solid line there, the actual signal y of t. Now, to find the spectral plot, we need to remind ourselves of what x1 and x2 look like in the frequency domain. So x1 for omega looked like that. It was just two impulses at minus 10 and 10. And x2 of omega looked like that. And what we're doing in the time domain is we're multiplying the two. So we've got a multiplication in the time domain. So the corresponding operation in the frequency domain will be a convolution. So I need to convolve these two. Now, we don't need to carry out a convolution integral. It's enough to simply visually shift the signals along. So a convolution will mean that we'll have a spectrum here centered at 10 and another spectrum here, or another replica centered at -10. And you can label that x2 of omega. Another way of looking at this is using the frequency shift property. So the frequency shift property of the Fourier transform says that when you multiply by a cosine, which is what we're doing here, we're multiplying by a cosine, it causes the spectrum to shift in frequency. So this is the shift in frequency, a positive shift and a negative shift. So whether you look at it as a frequency shift property or as a convolution property, the result is the same. Now the final section for this question is about Parseval's theorem. And we're asked for two things: to state it and to verify it. Now stating it, it's not enough to simply state it mathematically. We need to state the actual theorem. Then we need to verify it. By verifying it, we just need to demonstrate that it's true. So this is just a demonstration that it holds, or it holds true for this particular question. Okay, so let's first state Parseval's theorem. So Parseval's theorem, remember, it says the energy of a signal is independent of the domain in which it is calculated. So you need to state that and then state it mathematically. So the energy of a signal is independent of the domain in which it is calculated. Okay? So energy, independent, domain, those are the key words. And mathematically, we'd write it like this. Ex is the integral from minus infinity to infinity, x of t squared dt, and it's the same in the frequency domain. It's x of omega squared d omega, with the difference that there's a factor of 2 pi. Now, is it enough just to state this? It isn't. You need to state it both in words and mathematically. So for the next part, we need to actually demonstrate that it's true for this particular signal. So we will calculate the energy of the signal twice, and then show that these two energies are the same. So we'll say in the time domain, the energy, I won't use x, I'll say MEF, because the signal is called f of t, minus infinity to infinity So that's the integral from minus infinity to infinity e to the minus 2 at dt. And that gives you 1 over 2a. So that's the energy in the time domain. Now we need to demonstrate that the energy in the frequency domain is the same. So I'll say in the frequency domain, remember we had 2a over, no we didn't, we had 1 over a plus j omega squared d omega. So let's take a second to find the magnitude or the modulus of 1 over a plus j omega. So we can simplify this by multiplying by the complex conjugate. So we'd have 1 over a plus j omega times 1 over a minus j omega. And that gives us, or a, of course, we'd multiply numerator and denominator, so you'd have a minus j omega over a squared plus omega squared. Now, because we're trying to find the modulus here, or the magnitude, we would take the real part and the imaginary part, and that simplifies to 1 over square root of a squared plus omega squared. And that is what we replace in there. So I can now write this as one over a squared plus omega squared d omega. Now, this isn't a particularly easy integral, but the question tells us, as it'll hint here, that we can use the result that it's 1 over a inverse tan x over a. So we can simply put that result in there. So it's 1 over a times tan inverse omega over a from minus infinity to infinity. Now remember that the tan inverse of infinity is pi over 2. The tan inverse of minus infinity is minus pi over 2. Your calculator won't give you these values. So we can plug those in there, and we get 1 over 2a into pi over 2 minus pi over 2. And that simplifies to 1 over 2a. So that 1 over 2a is the same as the expression we found in the time domain. So we can say that the energy in the time domain equals energy in the frequency domain. Therefore, Parseval's theorem is verified. therefore, it's only verified for this particular function. We haven't proved Parseval's theorem. We've just demonstrated that the energy in the time domain here and the energy in the frequency domain here are the same. So it isn't enough just to find the two energies. You have to show that they are the same. And that's the end of part E, and that's the end of the question.